start off with is a little bit of an introduction. I guess you all know the story of the three bears, Goldilocks and the three bears. Is everybody aware of that story? Okay, all right. Well, Goldilocks and the three bears, it's a little bit like that in terms of renewable energy in remote grids or weak grids. What I'm going to talk about today does have a direct bearing on the main grid and microgrids in main grids, but for the moment let's just move to the obvious areas of weak grid and renewable energy in weak grids. So if we know the story of Goldilocks and the three bears, if you have a little bit of wind power going into the grid, like Goldilocks and the hot porridge, what you've got is a fairly ineffective end result. You've got small amount of renewable going in, ineffective in the sense you're not really saving too much in the way of real benefits in terms of fuel on the grid. Likewise, there's an opportunity, and some installations you'll find have done that. They put a lot of renewables, so they have a large wind farm, for instance, in a microgrid. Now, a large wind farm in a microgrid is kind of like the really cold porridge, because what happens is you're wasting all of that energy. When it's really windy, you've got to turn the wind farm back down and you're just wasting renewable energy. But there's actually a sweet spot. There's a Goldilocks position in integrating renewable energy into weak grids. There's a Goldilocks position with every renewable energy application. It's more particular in remote areas. It's more particular in weak grids than it is in a large grid, and that is a position whereby you've invested your capital, you've got your renewable energy plant, and you're getting the maximum benefit out of that plant. So we want that Goldilocks position, okay? We want to put as much capital into the renewables as we can, but we've got to get all the energy out of that deployment, out of that capital. We don't want to put in too little because that's not going to give us much of a return. We don't want to put in too much because that's wasting capital. So this whole talk's about the Goldilocks position of getting what's called maximum penetration or high penetration of renewables into the grid, the Goldilocks. And the reason why ABB's involved is because the Goldilocks position of renewables into these grids has a problem, has a serious problem. And the serious problem is the fact that the renewable plant, whether it's wind or whether it's solar, actually produces fairly poor quality electricity. Okay, we've got difficulties of voltage, we've got difficulties of frequency whenever we're starting to really push renewables into the grid. Some people have experienced that, maybe some people haven't and don't think it's a problem. It is a problem. So the first problem that we grapple with is voltage. As soon as you start pushing a lot of renewables in energy into the grid, you can see fluctuations in voltage which are outside the utility standard. But the same happens with frequency. When you're pushing a lot of real energy into the grid, you'll get frequency going outside of the grid specifications. So what's the one thing that's going to act if you push voltage or frequency outside of the grid specifications? The protection. So the protection of the network is going to act very quickly and you're going to get blackouts. And that's what you'll hear. You'll hear stories of people that are putting a lot of renewables into these weak grids, and you'll hear about blackouts, hear about outages occurring as a result of their renewables going in. So that's what we're talking about today. We're talking about what's ABB's solution to the out-of-utility drivers by renewable energy in the Goldilocks sweet spot of a business case, okay? So what we're talking about is microgrids and renewable energy, facing the new complexities in this particular sector. But just to simplify the whole talk, we're talking about that Goldilocks position, maximising renewables, the problem that creates, and ABB's solution. What ABB is doing is following up and growing and expanding what my company, Power Corp, initiated and worked on for 25 years, and that is becoming an integrator, okay? So we're an integrator who helps to enable the transition from fossil fuels to renewable energy, okay? And we're specialists in high penetration of wind or solar into these weak grids. So that's encapsulating what I just said there about the Goldilocks position. We're really trying to enable this renewable energy penetration. And why we're doing it, one of the things that we've realised, and we all realise, is that the cost of fuel is going up over time. The high spike there was that terrible case when fuel got to $150, $160 a barrel. But what we've done is work out, and we know that wind energy is cost effective against diesel fuel in around the $80 to $90 a barrel, for argument's sake. So in other words, if we know that if oil is at $80 or $90 a barrel, then wind is actually cheaper than diesel to generate. Solar is not much worse. It's a little bit above wind. In fact, the solar cost is coming down now with the cheaper panels that are around the place. So what we're saying here is that renewable energy with solar and wind is actually cost competitive against diesel fuel in these weak grids today. So again, we've got another driver to hit that Goldilocks sweet spot of maximising the input from the renewables, getting the maximum benefit back. That's what the business case, that's what the developers want to do. They want to get that return for their business case, maximise the amount that they get out of their investment. And ABB is here to enable that, as I said a minute ago. What we're seeing is normal integrated system. Obviously, down the bottom you've got your diesel plant and the load. Up the top, a solar farm or a wind farm. That's what you would expect to see as a renewable energy, fossil fuel power system. Diesel generators, we don't want to decry them. They're a very, very good source of energy. They have and are continuing to provide the bulk of electrical supply to remote grids throughout the world, and will continue to do so for a long period of time. They've got a lot of advantages over the renewables. They are obviously producing high-quality electricity. They don't have the problem typically of stepping outside of the utility standards. They are incredibly reliable and obviously on demand. What we're really trying to do is to move from this situation where the diesel plant is the large majority generator and the solar wind farm is the minority. That's one of the non-Goldilocks positions, through to this position, which is the Goldilocks position. So what we're looking for is to maximise the solar and wind, maximise the renewable, but again hitting this sweet spot of getting the maximum return out of these facilities. I can't stress it strongly enough. You will see examples, or you will hear of people claiming to have high penetration renewable systems working reliably, but if you look carefully you'll find they've actually over-engineered it. They've put far too much. St Paul Island, for instance, in the Bering Sea, is a classic case where you'll see often it claimed as a very successful high penetration renewable system. In fact, they've got about 3 times more wind power than they can ever use, and they're dumping wind power all the time. So yes, they're getting an electricity supply to the community, which is satisfactory, but they've over-engineered it. They've spent way too much money on the wind plant. Okay, so that's a non-Goldilocks situation. This is what you actually see out of the wind plant. Now this is actually typical out of every wind generator. We discovered nearly 8 to 10 years ago that you can lose up to 80% of the output of a wind turbine and have it come back in under 3 seconds. So any wind turbine put out in the wind farm will actually lose and regain its rated power or its output power over that sort of time base, over a few seconds. The reason why that's the case is because the rotor that's made at the front end, that's the propeller bit, is very lightweight. It doesn't have much inertia. The manufacturers don't want inertia. They don't want weight in the rotor. They design it to be very lightweight. The reason being is because of the cube law, you're getting a lot of power out of gusts of wind. They're pumping energy, if you like, out of the wind into the grid. Now, if the grid is really strong and solid, that doesn't matter. This sort of fluctuation doesn't really matter if you've got a wind farm in a made central grid. But as soon as that grid becomes weaker, as soon as you're starting to push a lot of renewables in And we are actually starting to see it in Europe, for instance, in Germany and places like this, where you're starting to see a lot of wind farms. You're starting to see it on the main grid, but obviously off-grid, when you're talking about these weaker grids in remote areas, you see it very, very quickly. You see this sort of fluctuation causing disturbance on the grid. Okay? Now, clearly, if you're actually losing 80%, 50%, 30% or whatever of the output of a turbine and having it come back again, that's real energy that's gone. That's real energy that's not on the grid. That will be reflected into the grid. Now, these are modern machines with modern control systems. It still applies. And if the solar boys think that they're out of the woods, they're not. Okay? This is the solar array. This is real data from real systems that we've put in. And you can see, in fact, with the solar PV, there are times when you actually get well in advance of the output rating of the solar array. You can get up to 130, 140%. And that's due to reflection off the clouds. So a flat plate collector out there on a cloudy day will get bounced back from the clouds and actually produce more than its rated capacity. And, of course, you can actually see the clouds come across and drop the incident radiation down. The concentrating collectors like the Greenvolt ones around the back here don't see the over-generation because they're particularly focused on incident radiation, but they will absolutely see the loss of generation on a cloudy day. So the solar boys that seem to criticise the wind boys can't get out of the problem, okay? What we're trying to do is to integrate the system together, recognising that there's a problem in the wind and the solar if we're going to wind it up to the Goldilocks position. And why do we want to get to the Goldilocks position? This is a summary of what I've just said before. If you have no integration and you're putting in a small amount of renewables, say 20% at the front end, and you'll often hear that. You'll hear people say, oh, well, we'll just put a couple of wind turbines into to this particular grid. It's really not worth doing. It's really not worth doing because all you're going to look at is 7 to 10%, something in that sort of order. Don't take these figures as being absolutely categoric. They're indicative, but they're pretty accurate indicative numbers, that you're going to see 7 or 8% fuel saving over the year. I mean, why would you bother doing it? Why would you bother going to a remote area to put a couple of turbines in to save 7 or 10% of the fuel? I mean, the effect is really not that great. However, if you get to the Goldilocks sweet spot where you get up to 100% penetration, which is what we can do with ABB's integration technology now, you can look well into the 60% fuel saving. Now, if you can go to a remote community, a remote mine, a remote town, and you can actually tell them that you're going to cut their fuel bill in half, if you're going to save 60% of their fuel, that's substantial. That's worth doing. Okay? Now, to do that and at the same time get the maximum business case out of the whole investment, we've got to hit that, as I said, Goldilocks position. We've got to solve this voltage and frequency problem. ABB solves the problem through grid stabilising, control and automation, and system simulation. They're the three things. So I just want you to understand, very basic, if you go away from this talk with nothing less than understanding if you stabilise the grid and then do the energy equation and control the energy flow, you've got the answer. And that's what ABB can do. We stabilise the grid with this device. These are two ABB inverters and a flywheel. Power Corp, my company, over the last 10 years of doing this, was using ABB inverters. We had a very close association with ABB out of New Zealand and worked very closely with those engineers to develop this technology. This technology is now owned by ABB, and the fundamental truth in this is that it's so fast acting. What we had to do, we had to be able to move energy in and out of that flywheel an order of magnitude faster than the problem. So we're able to move megawatts of power into and out of the flywheel in 5 milliseconds or faster. So by being able to move the energy in, the real energy in and out of the flywheel in less than 5 milliseconds, we're an order of magnitude faster than the problem, which means we can solve the problem that we discovered, which is this drop, which is this coming and going of power out of the wind or the solar. Okay? So this is a shock absorber. This is a shock absorber based on ABB inverters that can produce bidirectional real and reactive power. The reactive power is clearly managing the voltage. The real power is managing the frequency. It's pretty basic, it's pretty simple. This is not la-la land. This is nothing really out of the box, except for the intelligence in the inverters to be able to act so fast and to do this at a speed which makes sense. But in terms of basic thinking, what we're talking about here is simply a very fast-acting, bi-directional, real and reactive power source. And obviously the reactive power source you can imagine is a STATCOM. Yeah, of course it is. It's a STATCOM. Okay, so it's a STATCOM plus real power injection and rejection. Okay? Why don't we use batteries? And this is a big story. A lot of people will say we should be using batteries. Batteries are the way to go for this sort of application, and they're not. Batteries are very good for storing energy and redelivering energy, but they're not good devices for stabilising energy. And I would like you to go away from today's talk understanding to split the problem of stabilising the grid from the problem of energy storage. If you can understand that you break that nexus and you don't use batteries to do stabilisation, and indeed you wouldn't use the flywheel to do energy storage. Okay, so you understand there are two problems here in these remote grids. There's a problem of stabilising, there's a problem of energy. Batteries are good at energy. I'm not against batteries. Batteries are great and I support them, but use them for what they're intended to be used for. If you try to use a battery of any nature to do stabilisation, you'll put that AC signal that you saw before on the battery and it won't last very long at all. It'll do it for a little while, but it won't last too long. Obviously, a flywheel can take an AC signal beautifully. That's exactly what they're good for. They'll put power in and take power out at the same high-speed rate and do it very well. This is what we can show you happening. The red curve there is the wind speed going up and down, as we saw before, and the blue is the flywheel, taking power in and putting power out, charging and discharging all the time, backwards and forwards, countering that signal that you saw before. Think of it as an AC signal. Think of that mess that comes from the renewable energy as an AC signal. And you tell any battery manufacturer you're going to put an AC signal on their battery and see how long they smile. Well, they won't smile very long at all. But it's the problem that people haven't realised. They haven't understood the nature of the problem. Now we understand the nature of the problem. We've got a solution and life's pretty good. Okay, we've got a power grid, a micro power grid that we're going to be looking at in terms of the fluctuating of the power. Obviously looking at the flywheel down here, as we've said, generation, different sorts of generation, and also on the load side. We also have a communication link to solve this problem. So we've got the little computers. It's a distributed control system. So we've got two sides to this. We've got the power grid control, which is the stabilising, and we've got the communication network to do energy flow management. There's two sides to the story, and the control and the communication network. No central computer, it's distributed control. This is all established, it's out in the field working. I'll show you some examples in a minute. Okay, the history very quickly of what we did over the years that ABB's bought into. Way back in 1990 was when we were working on diesel stations. My team, my company comes from the diesel power station area. We come from running real power stations, and we've gone into the renewable space. So the generation goes through 1998 right through to 2010, up to 100% penetration. This is now some examples of what we've done. This is in the Antarctic at Ross Island, or the McMurdo base. So those of you from the US will appreciate that the McMurdo base in the Antarctic is a pretty important base for the US. And for us, as a small company in Darwin, to have won the contract and to be successful in doing that was a great feather in our cap. And now that's all over to ABB. So ABB now has the right and privilege to be able to claim this as a good example of ABB technology, which it should do, because the frequency converter, which is over there, that's the frequency converter which connects the New Zealand base, which is running at 50 hertz, and the American base, which is running at 60 hertz together, is all ABB technology. The power store, which is that flywheel inverter system I showed you a moment ago, is all ABB drives and inverters. The wind turbines are Enercon. Enercon put the wind turbines in, but we did everything else. Did all of the grid integration and the grid stabilisation. This is the Ross Island station, obviously flown down there in the C-17s with the US. As I say, we're very proud of this particular installation. Been running now for many years and doing very well. They're now looking at increasing the size of the wind farm. There are times in winter when the wind farm, even just those 3 turbines, will actually do a majority of the energy generation, but they're looking to expanding the wind farm now to doing most of the generation for that base throughout the year. This is a solar station in Marble Bar in Western Australia. Very hot. In fact, it's the hottest place in Australia. The PV tracks and delivers power to a full-size normal town with all of the normal facilities you'd expect. And during the day, we can turn all the diesels off. And the power from those photovoltaic panels can go directly to the town with no batteries. Remember, there's no batteries in this at all. This is just power directly, DC power from those panels gets inverted at the panel inverters onto the grid, and the mess that creates is cleaned up by the power store, that flywheel inverter system, to produce utility grade power, and it's fed to the town. Now, obviously, if the sun starts to go out or the clouds come over or whatever, there's enough reserve in the inverter, in the flywheel, to keep the town alive while it kicks in a diesel and a diesel will start up. Okay, but there's no batteries. That's the array. It's a 350 kilowatt PV array driving the town. Clearly, there's really no limit to the size of this thing. Once you've got the principle of that Goldilocks sweet spot, once you've got the principle that you're trying to solve utility disturbances, and once you understand that you're doing it with a very robust, reliable flywheel inverter system, the simplicity of it is brilliant. And now that's what we're rolling out in ABB, and we're really keen to sort of spread the message of a major revolution, if you like. The grid is back. I don't know that title is particularly appropriate, but certainly we would claim to have a high-quality grid now available for these situations. Locally, up in Canada, Madeline Island, if you know Madeline Island, out on the Gulf of St Lawrence, is planning to put in 6 megawatts of wind. They can put in 12. They may go to 12, but at the moment they're looking at 6 with Hydro-Quebec. We've been working with Hydro-Quebec for many years on that project, and they're now looking at putting in the flywheel inverter and control system to stabilise that grid to do exactly what I've just described there. So that's a local example which is coming up, which is reasonably sizable. That's a 64 megawatt heavy fuel power station, 6 megawatts of wind. They have a low load of 11, so 6 megawatts is starting to look a little bit above 50% penetration. Certainly if they go to 12 megawatts, they'll be going to 95% at times penetration. Very quickly, the last part of the talk is about the value chain. We have traditionally worked in all aspects of the design of these, from the consulting right the way through to the service at the end. That's what a schematic would look like, showing you the location of the small computers, those little blue boxes, at the various parts and pieces. The energy modelling, we've used Homer. We've worked very closely with Peter Linenthorpe out of Colorado on the Homer model. That's a computer system which is available for not a lot of money on the grid. It used to be free. It was developed at NRail. The professional version of that is now available. If you download that and work with Homer, you'll find that built into Homer is a lot of this flywheel technology that we're talking about, and you can use that for your energy modelling. More particularly, we do dynamic stability modelling, because clearly if we're talking about what is a very unstable grid situation, we need to model that. So we use Power Factory. We take data from the client. We'll run it through a Power Factory model. We've got most of the libraries for the wind turbines and things, so we can actually model the grid pretty easily, and we can come out with a pretty firm assessment of the sizing of the parts and pieces and what can be achieved on the particular grid. That's what the power store looks like schematically in a container, with the transformer at the end, the green bit, and the flywheel at the other end. What we have been able to do is to take the information from the power factory modelling, feed that directly into our control system, and come out with a full parameterisation of that control system prior to going to site. Clearly, as a extension of what I've just been talking about, is the rest of ABB's balance of plant, the EBOP that you'd call it, can be pulled through as well. So clearly, with the control system being able to manage reverse osmosis, water making, all the other parts and pieces that makes a complete system, there's a lot of pull through of ABB product as well, from the transformers, which would sit beside the wind turbines, right the way through to the switchboard and switchgear to go onto the grid. So the transformers, the switchgear, the other parts and pieces that ABB delivery is pretty standard, but we're now able to deploy that because we can actually stabilise the grid, we can make it all rational, and we can hit that Goldilocks sweet spot. So a couple of things to go away with is just to remember that if we're talking about these sorts of weak grids, indeed it will increasingly apply on the main grid, but from the weak grids, is we want to hit that sweet spot in terms of the utilisation of the renewable plant. If you're talking to a developer, that's what they really want. If you're going to do that, you're going to have to solve a couple of basic problems. If you understand that the basic problem splits into two, it's a stability problem and an energy problem. Batteries are great for the energy problem, control system for the energy problem, stabilising flywheel inverter system from ABB for grid stabilising, you've got the answer.